All right. So today we'll be talking about communication systems. So the progression of this course has been Fourier series, where we looked at the strength of harmonics in a periodic signal, and then we went to a Fourier transform, which was a little bit more general, where we found the Fourier transform of aperiodic as well as periodic signals. We learned a lot of properties that of Fourier transform, and we applied them during some examples as well as the homework problems. Now we are moving on to an application, and the first application that we are looking at is the world of communication systems. So when you think about communication systems, I want you to probably picture cell phone, you talking with your friend, or using the wireless channel. So, if you are interested in this area, then I highly recommend the next course that is essentially titled Communication Systems, which is ECSE 4520. The prerequisites for that are signals and systems and probability. So the title of that course is Communication Systems. So if you like what you hear today in terms of modulation and demodulation, how do I extract the signal from a carrier, and so on, I recommend you to take communication systems perhaps in the fall semester. So, before we begin today, let me, ask you, whenever you try to communicate between 2 points, what do you think you are trying to achieve? Right? What aspect of a communication system as a user you would be interested in as a user? Okay, so send a message, right? So reception. Is error okay? Is error okay during the reception? Or you would want that sending a message to be almost error free? So you probably want your communication, wherever you are sending that message to, and that whole transmission, which is the combination of transmission and reception, right, to the whole transceiver, you would want that to be error free, or at least the error should happen very, very, very rarely. And even if there is an error, there should be a way for me to correct that error. Right. So that's probably one. What else? What else would you be interested in? So data transmission and sending a message are kind of the same thing. But what aspect of data transmission would you try to maximize or minimize? Bandwidth, okay. So the data rate, right? You would want to have maximize bitrate, minimize latency. That's what Jacob says. All right, maximize bitrate is absolutely fine, and it is related to the bandwidth that you're going to use to transmit, and that relates to the data rate. Mbps, I no longer want megabits per second, I want gigabits per second, and perhaps in some time I will want terabits per second. So I want to push the envelope on that data rate aspect, which is directly related to, as Ryan suggested, the bandwidth. And I'm going to write bandwidth in terms of in red. Max says signal to noise ratio. Perfect. I want signal to noise ratio. Minimize or maximize. What should I do with signal to noise ratio? I want to maximize signal to noise ratio. Okay, so what should I do if I want to increase the signal to noise ratio? Let us say this is signal to noise power ratio. What should I do? I can increase signal power or I can decrease noise power. Decreasing noise power, you can do that using signal processing techniques, improving the channel. You can do a lot of things to reduce noise power, because if you see this, signal to noise ratio is signal power divided by noise power, right? So if you want to maximize this entire thing, then you can do it using signal power increase, or you can decrease the denominator, which is noise power. So if you want to decrease the noise power, which will also help with making this error free, you can try to improve various aspects of the channel. Maybe improving the quality of the channel, maybe putting some signal processing blocks between the transmitter and the receiver chain, right? So you can process the signal better, perhaps. But you might end up with a limit, right? That noise power you might hit a wall, and that wall might mean that you no longer can decrease noise power. So what's your alternative? If you keep uh, desiring better signal to noise ratio, and if you hit a wall with the noise power, then your only option is to increase signal power. What does that mean? That means shout louder, right? Like increase the transmitted power. Well, can you do that in an unlimited manner? Perhaps not, because otherwise your battery on the cell phone will die out much faster. So power, which is a very important resource for you as a communication systems engineer, power and bandwidth will probably be the most important resources. And who controls the bandwidth that you use? Well, the Federal Communications Commission, right? FCC controls the bandwidth that you use. The FCC is going to allocate some licensed bands and some unlicensed bands for experimentation. But those licensed bands that all these internet service providers like Verizon, Sprint, and so on, they pay money to buy a slice of the spectrum or the bandwidth that is through the FCC. So that's a very, very expensive resource as far as these internet service providers are concerned. Clara says, would you noise limit be 0? Well, nothing is 0, right? So if the noise limit is 0, then it's a theoretical limit, but in practice it will never be 0. Remember, if no matter what you have, you will have some noise, and that noise, ideally, yes, absolutely, ideally you would want the noise to be 0, but you will never be able to get that, because there is thermal noise, which depends on the temperature in which you are operating your transmitter and receiver. And noise could come in through the channel, noise could come in through any sort of distortion. Even if you imagine like a screw, right? That screw which connects 2 points, for example, that can give you some noise. So noise is inbuilt to systems. Ideally, theoretically, you can say it can go to 0, but practically it can go very, very, very small, but it will not go to 0. And when you turn on, say, a spectrum analyzer, you can see that there is a noise floor, right? And that noise floor is essentially due to the thermal noise of the measuring device. Max says you can balance transmission medium to eliminate noise is a theoretical concept. Minimize noise is a practical concept. Yes, mitigation is fine. Minimizing is fine, but eliminating noise can only happen ideally, like not in practice, because that would mean that if just imagine, if you want to make thermal noise zero, thermal noise is present everywhere. If you want to make thermal noise zero, then you have to reduce the temperature of operation by a lot, and that might not be practical. So if I say that you can use your cell phone, but you have to use it from a freezer, you will probably not appreciate that, right? So there are limitations on how much you can reduce noise. Completely eliminate it, just a theoretical concept. All right, so let's see. For the user, we talked about error-free transmission. You want things to be really, really fast. So I have to pay money to the FCC to buy some bandwidth. And I also, don't like the circle that keeps going round and round on YouTube, right? Like I want fast. I want to be able to stream data. I want to be able to look at 60 frames per second or very high quality data in a manner of live streaming. So I want to be supported by a high data rate. And the third aspect we looked at was signal to noise power ratio. So I might have a limitation on how much noise I can reduce. And another way I can increase signal to noise ratio is by increasing signal power, which means that my transmit antenna is sending out a more powerful signal, which means that I am going to run out of battery on my transmitter, right? Which is what happens, right? When you take your cell phone to a remote area where the closest cell tower is, probably farther away, then you tend to lose the battery on your cell phone much faster because it's trying to communicate with the closest cell tower, and it's not near. It's in a remote location, for example. All right. Let's see. So let's begin with these ideas and see what you were saying that before. Higher frequency antenna is smaller, but for more power antenna, right? So there is a relationship between antenna size, frequency of operation, and the range. So suppose I wanted to increase the frequency of operation, right? Which means that instead of having a slow carrier, I have a really, really fast carrier. So let's suppose instead of using microwave frequencies for wireless transmission, I want a light carrier for optical transmission, right? So by going from microwave to light, all I did was increased the frequency of my medium, the carrier, by a huge margin, maybe from a few gigahertz to hundreds of terahertz for light. So when I do that, when I increase that frequency, my antenna size consequently can go smaller. And the reason is the antenna size is related to the wavelength. So you will design maybe half wavelength antennas or maybe quarter wavelength antennas. So the higher frequency that you have, the antenna size can go smaller, which means that you can carry it around in your pocket, right? You don't have to have a huge antenna connected to your cell phone. So that's a benefit of going to higher frequencies. And you have to go to higher frequencies if you want to deal with aspect number 2, the data rate. But the problem of going to higher frequencies is the range goes down. So the range between point A and point B over which you are trying to communicate goes down. So you will have to increase your transmit power, right? You will have to increase your transmit power to compensate for that, or you use repeaters, right? So you use multiple repeaters between the two devices that you are trying to that are trying to communicate with each other to make sure that there is that signal goes through to the receiver. And in reality, we use repeaters. So if this is an optical transmission, repeaters are I believe every 80 kilometers. So every 80 kilometers, you will see a repeater where you actually regenerate the signal, and we are able to regenerate the signal because, in today's world, we do digital communication, not analog communication. So you will be able to regenerate those zeros and ones and have a repeater every 80 kilometers. But all these aspects are related to each other. Okay, I think we need to kind of move on now and start looking at this relationship of antenna size and the wavelength and frequency of operation. I believe you guys see that in fields and waves, perhaps. Let's see. So this is a diagram of what we have been discussing, right? So this is your message, M of t. M of t is your modulating signal or the message that you're trying to transmit. So this is essentially your voice going into a microphone that you might be interested in transmitting from point A to point B. So let's say I have point A right here, right? This is point A and point B is right here at the very end. So that's your point A to point B. And just for this discussion, we are assuming that our communication is wireless. So we are using the radio frequencies of the range 200 megahertz to 300 gigahertz. Those are the frequencies that you might choose to transmit from point A to point B, like in the wireless medium. However, the message itself is of much slower rate. So your voice can only go from maybe like 200 hertz to 4 kilohertz. Even though humans can hear, you can hear 20 hertz to 20 kilohertz, you can only say things that are in this range, 200 hertz to 4 kilohertz. So that is much lower than this range, right? It's much lower than that range. So you see what happens here. The signal that you're trying to transmit using a carrier, the carrier right now are the microwave frequencies. In the previous class, we talked about throwing a stone and the fact that you will be able to throw the stone properly if you had tied it on top of a stone, right? So the stone was the carrier, the piece of paper itself was the message. So the voice is our message and the microwave frequencies are the carrier here. So we are essentially modulating the carrier or changing some aspect of the carrier, maybe amplitude, maybe frequency, maybe phase, to transmit our voice. But there is a clear separation in the frequencies that are representative of the signal and the carrier, the message and the carrier. In that the message is much lower in terms of its frequency. And if you went to light frequencies, those would be of the order of 192 terahertz. So in that case, your message frequencies can also now go up because of that, and we'll talk more about why it can go up in just a bit. All right, so let's come back to this diagram here. Let me box this up as 1 because this is my transmitter. So that's my transmitter. What do I have in my transmitter? I'm not showing amplifiers and pre-compensation signal processing. So I'm not showing a lot of things that actually happen. I'm just showing you a basic transmitter that can do amplitude modulation. Modulation is changing some aspect of a carrier signal. The carrier signal right now we are using is called C of t. So we are changing some aspect of the carrier signal based on the message that we are trying to transmit. This will get a little bit more clear once we start seeing the waveforms. But if you wanted to do amplitude modulation specifically, what you're trying to change is the amplitude of the carrier based on the modulating signal or the message signal. And we do that by simply multiplying them together. So this is my analog multiplier. In a mathematical way, it's just multiplying the two time domain signals, M of t and C of t, message and the carrier. This carrier signal is a periodic signal and it comes from a local oscillator, which means that you can use a function generator. Given a frequency, you can generate a cosine omega naught t, for example, right? So you can generate cosine omega c t, c standing for carrier, right? Or it might be e to the j omega ct. It might be a complex exponential, or it might be a real carrier signal as cosine omega ct. But that's periodic, and it is generated by a local oscillator at the transmitter side. You multiply those two together. The moment you multiply the message and the carrier, you get a modulated signal. That means that now you have changed the amplitude of C of t depending on M of t. You have modulated the carrier, which is essentially written as S of t, the signal that we are trying to transmit, is the product of the message and the carrier. Blue here, yellow here. Next, you use an antenna to transmit that signal, and then somewhere, close to point B, you have a receive antenna that is essentially tuned in such a way that it resonates with the frequencies of the carrier itself, so as to pick up those frequencies. So you have this receive antenna here. And if we did this in a perfect world, if you transmit S of t, you get S of t here. Practically, you might have some S hat of t, right? We are assuming right now that there was no change in the signal when you did the wireless transmission. Just for the purposes of discussion, we are assuming that whatever you transmit is what you receive here. And then you will have amplifiers here, you will have filters here, you will have a bunch of components that will make up your receiver. But we are just showing the important aspects, the absolutely important aspects. Max says the lecture isn't being recorded. So Max, I changed the way we record things. It is being recorded, just not through WebEx. Let's continue here. I have the receive antenna that comes in, and I'm assuming that there was no problem during transmission. I sent S of t, I got S of t. It practically doesn't happen. You get something different. But your goal is what? Your goal is to match these two, right? So your goal will be that at the end, point B, whatever point B is, V sub O of t matches M of t, the message that you are trying to transmit. That's your primary goal, because in step 1, you guys said user is interested in receiving the message. That was your point number 1. And that gets completed if VO of t is as close to M of t as possible. All right, let's move on here. So what do you need to do so what did we do in the transmitter? We modulated the carrier, right? Now we need to do exactly the opposite. So we need to do the amplitude demodulation, which means we need to extract the message or extract the information from the high frequency carrier. So first, in the transmitter, you put the message onto the carrier. Now you are extracting the message from the carrier. Exactly the opposite. And the way you do that is by again multiplying by the same periodic signal C of t. So this is now the same signal at least as close to the local oscillator that you used in the transmitter as possible, right? So ideally this guy matches this guy. But practically there are some issues with that. Like, it doesn't happen right away. Why can't you divide by C to recover M of t? Well, the way you do that recovery is by using an analog multiplier, right? So if you were trying to do this using some signal processing algorithm using a digital computer, fine, you can do that. But I'm going to use analog components to perform this demodulation. So I'm using an analog multiplier again in the receiver side to do that multiplication operation for me. Oh, so that's so Clara, you bring up a very, very important point. Is C of t derived from the same local oscillator? No, it's not, because it's a local oscillator, right? The key term here is local. So we used some oscillator at the transmitter side to generate the first C of t. What does a periodic signal have? Well, it will have some frequency and it will have some phase. So if I give you the information about frequency, 1 kilohertz, 10 kilohertz, 10 megahertz, you will be able to quickly generate a similar frequency local oscillator in the receiver side. All you need to know is the frequency. So to match in terms of a frequency is pretty easy. However, in order to match with the phase, it is very, very difficult. So actually we will revisit this topic of synchronization in phase of the local oscillators later on in the lecture. But it can have a very, very dramatic effect on the signal reception. In fact, for certain phases, you may receive nothing, absolutely zero. It might cancel out completely. So you will have to probably use a phase locked loop, PLL, to make sure that your transmitter and receiver are matched up in phase. Or there are other schemes as well. If you are interested, let me know. But there are too many things in terms of phase synchronization that we could go over. All right, let's move on. Here we have assumed that C of t at the receiver and the transmitter are sort of matched up in frequency and phase both. Easy to match in frequency, not the case for phase. So assuming that this is my S of t and this is my C of t, I use another product multiplier here to demodulate. So amplitude demodulation. What do I get? I get V of t, which is M of t times C squared of t. The reason for that is S of t is M multiplied by C. M of t multiplied by C of t. So if I multiply with C of t again, what I get over here is M of t multiplied by C squared of t. Then when I multiply with a cosine again, I actually get the sum frequency terms and the difference frequency terms. The sum frequency terms will appear at twice the frequency of the carrier. So they will appear at 2 times omega c, and we will look at it mathematically in just a bit. And I don't want that. I can remove those because that's not of interest. What I'm interested in is the demodulated message at baseband, at zero frequency. So I use a low pass filter to extract my message. The low pass filter, say I have some frequency omega f. I'm going to call this cutoff frequency of my low pass filter to be omega f or omega c, whatever that is. And I'm going to make sure that omega f is chosen in such a way that it does not allow 2 omega c to go through, but it does allow how much? Let's say our message signal is between negative omega m and positive omega m, where m is being used for message, right? So I'm essentially band limiting the message signal to plus and minus omega m. Omega m referring to the highest radian frequency in the message. So that will have to go through to this. So omega m will have to go through, but the 2 omega c term will need to be rejected. And that's how you would choose omega f, the cutoff filter, the cutoff frequency of the low pass filter. And if you did all of that, you get v sub o of t. And if we did everything right, then this has to match with that, right? So that's in a nutshell what your communication system, all the various aspects of communication system that we are going to look at here. Okay, let's move on and try to understand this a little bit better by looking at time domain view of signals. This is my transmitter, right? Bare bones of my transmitter. I'm just essentially taking the message, multiplying it with a cosine carrier. It's periodic, and I'm transmitting it. So suppose my message looks like this, right? This is my message to be transmitted. It could be a voice signal, for example. And I hope you notice that I have chosen m of t to be very slow in comparison with my periodic carrier signal. And the reason for that goes back to this microwave frequencies versus voice frequencies. And the fact that I'm going to be interested in the signal that I try to transmit is probably not going to be of higher, very, very high bandwidth in comparison with the carrier signal itself. So the carrier tends to be a very, very high frequency signal in comparison with the message. And when I multiply these two signals together in time domain, in frequency domain, there's a convolution that is happening. But over here, we are just focusing on the time domain view. What happens is you will get that carrier on signal in S of t, but you see what happened here. The amplitude of the carrier was constant. It was not changing. But now, once you multiply these two together, it started changing. Amplitude got changed depending on the message signal. So we are trying to, this is what we mean by amplitude modulation. Change the amplitude of the carrier signal depending on the message. So where is the information? Information is in the envelope of the carrier. Now, just for the sake of, comparison, if we were doing frequency modulation, how would things look like? Well, if this was your message, say going up and down, we would be changing the frequency of the carrier signal. In this case, we are not changing amplitude, right? So low frequency here, highest frequency here, and then back to low frequency there. So you would look like, low frequency here, and then no change in amplitude, but low frequency, and then it'll go high frequency here, and then it'll go to low frequency here, right? So low frequency to a high frequency, and then linearly goes down. That's a chirp signal. A chirp signal is a linear increase in frequency. So that's how we would do frequency modulation, changing the frequency of the carrier depending on the message. You can actually do phase modulation as well, changing the phase of the carrier depending on the message. So if you think about just binary transmission of 1 and a 0, send maybe a sign here and send a negative sign over here, right? These are lining up. So over here, the phase is 0. The phase over here becomes pi, right? So you can change the phase of the signal as well to indicate the message. I've just shown it for digital purposes over here, but we are talking mainly about analog communication here. Question in the chat box: how do you determine the envelope of M of t signal for S of t? Yes. That's where we are going. Now, transmitter is fine, right? Multiply the signal, we change the envelope of the carrier signal. So my S of t looks like a signal which has a frequency of the carrier, however, its amplitude changes based on the message signal. Also note that this M of t, this guy, right? You do not want this point to cross over onto the negative side. You don't want that to happen. If that happens, then you will get a signed reversal in the signal. So you don't want that to happen. We will talk about that again later on as well. Okay. Now let's try to do a time domain analysis, and our goal is to find whether VO of t, is it equal to M of t or not, right? That's our goal. Whatever we transmitted, is it the same thing as we received or not? Let us try to prove that. But we are trying to prove that in a bad way first. Why is this a bad way? Because it becomes very, very messy mathematically to prove that or to analyze this in time domain. So let's take a look. You have the transmitter on the left, you have the receiver on the right. All these pieces are exactly the same as we saw earlier. You have a message signal, voice perhaps. Then you have a cosine, periodic, high frequency carrier. Multiply them together, transmitted using RF frequencies. You received them, and in this case, we are assuming that the reception is perfect. Then to extract information from S of t, we had to multiply by the same local oscillator again. We got V of t, then we did a low pass filter with H of omega. The frequency response of the low pass filter is given over here. It's an ideal low pass filter to get VO of t. So let's do a time domain analysis on this. We start with V of t. V of t is S multiplied by C. So S of t multiplied by C of t. We can write S of t as M of t multiplied by C of t, cosine omega ct, which means that V of t, all right, let me actually do this. This is what? This is M of t, the message, multiplied by C of t. So we multiply by C of t again, you get M of t cosine squared omega ct. Now this particular trig identity is going to be used many times. Cosine squared x is 1 plus cosine 2x divided by 2. You will use this trig identity many times. M of t remains as is. Once you have that, expand it out into two terms. What do you have? You get M of t divided by 2 plus M of t multiplied by cosine 2 omega ct divided by 2. So you got something at baseband. Baseband, we'll take a look at what baseband means in just a minute. That's your half of the message. That's your baseband. Half of the message, right? M of t divided by 2. But you also got something at twice the frequency. I should probably reverse these. I should probably highlight this in green because that's what I'm after, and highlight this in pink so as to suggest that I can reject this because I am not interested in M of t multiplied by cosine 2 omega ct. I am interested in as close to M of t as possible. So this is actually at passband. At twice the carrier frequency. And this is where your low pass filter comes in. This particular h of omega guy will be used to pass m of t through. So the frequencies in m of t will have to be pass through omega f. So omega f has to be greater than the highest frequency in m of t. However, you want to reject this, right? Because in VO of t, you want that to be very close to m of t as possible. You just want this. Maybe you can use an amplifier to with a gain of 2 to get rid of that divide by 2 factor. So that's doable. Also note that the moment you start talking about amplifier or anything that you want to add to your receiver, you are increasing noise in the system. So as a communications engineer, your goal should be to have as less components as possible. Even if you think about signal processing, the more complex signal processing that you have, the longer it will take to process the signal. So you will try to minimize those aspects, right? You will try to minimize the number of components that go into your receiver, as well as the amount of signal processing that needs to happen for an error-free transmission. The problem is that the more number of components that you have and the more signal processing that you have, you increase the real estate of your receiver. The receiver will become bigger. It will become more expensive. It will become more complex. And also, it will take you longer for you to hear the message that was transmitted. So there will be a latency issue as well. So again, there's always a trade-off, right? Performance and cost. Okay, so let's go to the next step. Here we are trying to look at V sub O of t. V sub O of t is right here. We are trying to look at that over there. V sub O of t in time domain can be written as V convolved with H. So V of t is coming in. If you took the inverse Fourier transform of the low pass filter transfer function, you would get small h of t. If you have small h of t, you convolve in time domain, because we are trying to do a time domain analysis here, V of t convolved with h of t. All right, so that means what? You use the convolution integral, you write V of tau, h of t minus tau, d tau, integrate from for all time, which can be essentially written up as a, notice h of t. If this is a rectangle, your h of t will be a sinc. So we have essentially written up the entire integral, convolution integral over here, which I hope you agree is messy. So what do we switch on to? We switch on to the frequency domain analysis instead, which becomes much easier to handle. Note, and we have said this earlier, omega f should be chosen such that all the frequencies in m of t pass through it, but not 2 omega c. So the 2 omega c t term, we don't need that. We can reject that. But it has to pass all the frequencies in the message, because that's what we want. We want the output VO to be as close to m of t as possible. So it has to preserve the frequencies in the message. All right, questions here? All right, let's move on to the frequency domain analysis, because time domain analysis was messy. So frequency domain analysis, transmitter is shown here. Let us suppose that the Fourier transform of m of t is cap m of omega. We multiply that with c of t. C of t is periodic, and we'll prove this in just a minute, that if c of t is periodic, the Fourier transform of the carrier will consist of delta functions. We have actually seen this in the previous class as well, but we'll prove it on the next slide too. C of t is periodic. C of omega consists of delta functions. We are trying to multiply here, which essentially means If you multiply in time domain, you are trying to convolve what? You are trying to convolve m of omega with delta functions. And convolving with impulse functions is very straightforward because they only result in frequency shifts. Again, we'll take a look at that as well. But in time domain, it looks like s of t is m of t multiplied by c of t. So s of omega, Fourier transform of s of t is s of omega, which can be written as Fourier transform of m of t multiplied by c of t, which can be written using the time multiplication property as 1 divided by 2 pi Fourier transform of the message convolved with Fourier transform of the carrier. Now, you see, this is convolution with delta functions, right? M of omega, the Fourier transform of the message, is essentially getting convolved with delta functions, which results in just frequency shifts. That's it, frequency shifts of the M of omega spectrum. Again, we'll prove this later as well. So in the next couple of slides, we'll try to prove this and this. Let's take a look. The statement here is if C of t is periodic, then cap C of omega consists of delta functions. We can prove this using the exponential Fourier series. C of t is periodic, which implies that C of t can be represented by an exponential Fourier series as a summation for all k, a sub k e to the j omega naught t, where omega naught is 2 pi divided by t, where cap t is the time period of this periodic signal, C of t. Now, if we take the Fourier transform of C of t, which is C of omega, we get Fourier transform of all these exponential Fourier series. Summation a sub k e to the j omega t, j k omega naught t. ak doesn't depend on t. The only function that depends on t, which we need to consider for applying the Fourier transform, is e to the j k omega naught t. So I can bring in the Fourier transform operator inside. Once I do that, I'm interested in finding out the Fourier transform of e to the j omega naught t. This is a property, right? Fourier transform of a constant 1 is 2 pi delta of omega, which means if I use the frequency shift property here, I get Fourier transform of 1 times jk omega naught t will be 2 pi delta of omega minus k omega naught. Very similar to a homework problem that you guys are working on right now. Using this over here, I can say Fourier transform of e to the j omega naught t is going to be 2 pi delta of omega minus k omega naught, which comes up over here. Oh, I missed a k there. K there. Next, if I put this guy over here, I just combine them, right? Take this guy, put that over here. You get the result. Cap C of omega is 2 pi summation of overall k, a sub k, the Fourier series coefficients of the periodic signal, multiplied by delta of omega minus k omega naught. And as you can see, this only has delta functions present at plus and minus 1 omega naught, plus and minus 2 omega naught, plus and minus 3 omega naught, and so on, as well as k is 0. All right, so that's the first proof. Next proof is convolution with delta functions results in frequency shifts. Let us try to prove that. So if you want to write that property in a mathematical equation, you can write that x of omega, cap x of omega, convolved with a delta function, and the delta function over here is valid at omega equals omega naught, because delta of omega minus omega naught here equals x of omega minus omega naught. When we looked at the convolution with an impulse, perhaps a month ago, we saw that convolution with an impulse is pretty simple, and it only corresponds to time shifts. And those time shifts were there because the functions themselves were in time domain. Now the functions are in frequency domain. So when you convolve with impulses at certain frequencies, those will be corresponding to frequency shifts. So let's take a look. Proof. Recall that x of omega convolved with y of omega can be written as integration over all theta, x of theta, y of omega minus theta d theta, right? So that is essentially the convolution integral, but in frequency domain. So instead of tau, we chose theta, and instead of t, we have omega. Now, if we shift y, what do you get? Instead of omega, you have omega minus omega naught. If you shift that, this omega minus theta will become omega minus omega naught minus theta. That's it. Now, we don't have y, we have delta. So if you change the function from y to delta, what do you get? Negative infinity to infinity, cap x of theta remains as is. Instead of y, you now have theta of omega minus omega naught minus theta, d theta. So when is this valid? This is valid when the argument of the delta function equals 0, which means omega theta equals omega minus omega naught. So use that to write theta here. What do you get? Integration over all theta, cap x of omega minus omega naught, because you have now used this theta here. Omega minus omega naught, delta of omega minus omega naught minus theta d theta. Next, notice that this particular function here is independent of theta, so it can come out of the integral right here. And the rest is just integrating over an impulse present at some location. However, it doesn't really matter what location because you're integrating over all theta anyway, negative infinity to infinity. So that gives you a 1 there. So the result of convolving with an impulse is a frequency shift. X of omega gets shifted to x of omega minus omega naught. That's it. And that omega naught depends on where is that impulse. All right, so this matches, let's see, blue. This is coming from here. Okay, so using these things, let us take a look at amplitude modulation in the frequency domain. What is amplitude modulation? Changing the amplitude of a carrier signal depending on the modulating signal, m of t. M of t multiplied by c of t. In this case, we are assuming that it is a real signal cosine 10t. So the radiant frequency of the carrier is assumed to be 10 radians per second for this example. And then you transmit. S of t is m of t multiplied by cosine 10t. The Fourier transform of which can be written as in the frequency domain here. First, multiplication in time domain became convolution in frequency domain. So we are using the time multiplication property here, which is why we get an additional 1 over 2 pi factor there. M of omega, which is the Fourier transform of m of t. And then we also need the Fourier transform of cosine 10t. Well, the Fourier transform of cosine 10t is simply pi delta of omega minus 10 and pi delta of omega plus 10. So two impulses with a weight of pi present at plus and minus 10 on the omega scale, right? So that's your cosine, also proved earlier. So when you do this, now you can see that we are interested in m of omega being convolved with delta of omega minus 10, and we saw what happens. We just change the frequency shift. So omega, m of omega convolved with delta of omega minus 10 becomes m of omega minus 10. The 1 over 2 pi and pi, the pi cancels out, you get a half there, plus half m of omega plus 10. So this is like saying when you multiply a signal with a cosine, half of the signal gets shifted up to 10 and half of the signal moves down to -10, right? So we are up converting the signal from baseband to a passband. Let's take a look here. M of omega is assumed to be a triangle between -1 and 1. All of these frequencies are omega, omega, omega. If we start off with M of omega as a triangle, by the way, the message, I hope, what is the shape of the message? M of t? In frequency, M of omega is a triangle, which means that in time domain, the message is what? Function. Sync squared is absolutely right. So we have assumed that M of t is a sync squared signal, which means that M of omega is a triangle, and it is a very innocent looking triangle with a height of 1, and it goes from -1 to 1, right? So the highest frequency is 1 radian per second in M of omega. When we multiply this with a cosine present at 10 radians per second, what happens? Well, individually, if you take a look, C of omega, which is the Fourier transform of cosine 10t, will be 2 impulses with a weight of pi at 10 and -10, right? So those are coming from the pink piece. And M of omega, I was using blue. I did an assumption on that, suppose. Then when I convolve these two, what do I get? Half of it goes up to 10, half of it goes down to -10, right? So we up converted the signal. You see this guy moved up here, you get this, and this guy moved down here, you got this. You see this? Got up converted, right? Maybe I can draw the arrows here. Up converted. And that shift is 10 radians per second because cosine is present at 10 radians per second. So that's called, up conversion. Because in frequency, you pushed it up. This was at baseband, centered around 0 frequency, and this is at passband. The band that we are interested in is 9 to 11 radians per second. The center is 10 because the cosine is at 10. The width is 2, right? The width is 2 here because this width is 2. And again here as well. So when you do an amplitude modulation in frequency, that's what happens. The spectrum of the message goes up and down by the radian frequency of the carrier signal. That's it. So much easier to analyze things in the frequency domain here. So transmitter side, amplitude modulation. This is what you will transmit, right? This is what you will transmit, S of omega. Now, of course, there has to be a receiver side. And in the receiver, you do the opposite of modulation. You do demodulation, where you are interested in extracting the message from S of t. So in this case, you get the signal S of t, you mix it or you multiply it with C of t, present at cosine 10t, very easy to match in frequency. In reality, it would have been what? Cosine 10t plus some phase error, phi, right? Right now we are assuming that there is no phase error. Phi is 0 here. But in reality, there will be a phase error. All right, let's move on. After you multiply, you pass it through a low pass filter. The low pass filter has a height of 2, and it is specifically chosen with a height of 2 because remember earlier I said you are going to get half the message here and half the message there. So you wanted to multiply it by 2 by either putting a amplifier of gain of 2, or you can just increase the passband frequency, sorry, the low pass filter passband with a gain of 2. That's what we are doing here, just by scaling up the low pass filter. But it is passing frequencies 1 and -1. So negative plus and minus 1 radians per second. That is limited that way because it is directly related to the frequencies of the message. It is also chosen, so there are some problems, right? I could have chosen 2 radians per second here or 3 radians per second here. The only frequency that I should not select is what, 20 radians per second, because that is your twice the omega c. But I could have chosen 2, I could have chosen 3, but I chose to be at 1. Why did I choose to be at 1? Because all I was interested in was the signal between -1 and 1. So if I increase the low pass filter cutoff to 2 radians per second, 3 radians per second, and so on, I am letting the signal go through, but I'm also letting some of the noise go through as well, which I don't want. So I want that filter to be as tight to the signal as possible. Out of band noise should be rejected as much as possible, which is why we don't do it at 2, 3, and so on. Maybe if you wanted to have it a little bit of room, maybe you go to 1.2, 1.5 radians per second, but that's it. All right, let's take a look at the frequency domain analysis for this. S of omega from the previous slide, that's what you transmitted, was this. 2 triangles because the message is a triangle in frequency, present at 10 and -10 with a height of half. You are again trying to multiply with a cosine carrier, C of t here. The Fourier transform of cosine 10t, as we did earlier, is 2 impulses with a weight of pi present at plus and minus 10 radians per second. Now you're trying to multiply in time domain, which means in frequency domain, you're trying to convolve these 2 guys, S of omega and C of omega. When we convolve in frequency, what happens? You are going to have 4 pieces. The first piece is going to be this triangle convolved with, oh, come on. This triangle, let's see, erase this and erase this. The left triangle convolved with an impulse, right? What do you get? You get that guy. That's your first convolution, because you can break this up into 4 convolutions, right? Left triangle, left impulse, left triangle, right impulse, right triangle, left impulse, right triangle, right impulse. So 4 convolutions, but all those convolutions are with impulses, delta functions. So frequency shifts, that's it. So let's take a look. Left triangle with left impulse gave you that triangle there with a height of 1/4. Why did it become 1/4? Because every time you multiply, see, m of t multiplied by cosine, you got half m of omega. It is already half over here. So when you convolve with a cosine, it gets half again, so 1/4. Erase these 2 and take a look at this. Maybe blue. This guy with this guy, you get over here. 10 plus 10, 20. Height is 1/4, triangle shift. Erase, erase. Now there are going to be 2 triangles that are at DC, one on top of each other, one on top of the other, because of this triangle convolved with that guy, and this triangle convolved with that guy. So when that happens, 10 minus 10 minus 10 plus 10, they both fall at omega equals 0, but they are getting added up. So 1/4 plus 1/4, you get a half. That's the one that I'm interested in, right? That's the one that I want to get, because that's the message, the triangle. So when I pass it through h of omega here with a gain of 2, with an amplitude of 2 for the frequency response, that half gets multiplied by 2 to get a 1 there. And minus 1 to 1 is coming from v of omega. This is exactly the same as the Fourier transform of the message, which means that we were able to transmit things successfully. Now coming back to the question of, let me erase this here. Let me come back to the question of the frequencies in the filter, right? The plus and minus 1. The 2 is fine, the scaling is fine. But this, plus and minus 1. If we had widened the signal, if we had widened it to 2, 3, 4 and so on, you would have got the same answer here. The problem is that if there is any noise, say you have some sort of noise here, and you have a wider low pass filter, then you are allowing that noise to corrupt the message because you will let that through. That's called out of band noise. Out of band noise. Out of band with respect to what? With respect to the signal, right? It is outside the band of where the signal is. So if you increase the width of your low pass filter, you will allow those frequencies to go through, which will essentially just distort my signal. So my reception may not be error free in that case. So I would want that to limit that. So I'll come very, very close to 1. But if I come very, very close to 1, then I will be in a different kind of problem. The problem here will be, okay, can I practically make this very sharp rectangle filter? Probably not, right? I will probably have some pass band, some stop band, some transition band, some roll off. So if I have to have that, then maybe I need to relax that frequency requirement to maybe 1.5 radians per second. So in that case, I will let some small amount of out of band noise to go through, but I want to minimize that as much as possible. All right, questions here. Okay. Let's come back to the question that was raised earlier. Synchronization of local oscillators. What is the problem? So for this purpose, we have a transmitter on the left here. M of t is the message. The Fourier transform of the message is assumed to be a triangle between negative omega m and omega m. So omega m is right now the highest frequency in the message, right? That's the highest max frequency in the message, radian frequency in the message. You multiply this with a cosine omega ct, where omega c has to be much greater than omega m, carrier frequency much greater than omega m. That's the local oscillator at the transmitter. You send it across. You have a receive antenna. The first thing that you do in the receiver is, apart from amplifier and all that, like in terms of the components that we are observing, we are looking at the analog multiplier. Again, another local oscillator, I can easily match in terms of the frequency. So omega c is fine, but there might be some phase error, phase synchronization error. So I'm representing that by some theta. So that's your local oscillator at the receiver, right? Just think about it. If I say generate a cosine at 10 kilohertz, everyone can generate that, right? All you have to do is select the shape, cosine, select the frequency, 10 kilohertz, done. It will generate, right? The problem comes, when does that cosine 10k happen, right? Like when is that? Where is that in terms of time? What is the time delay, right? So the phase is what is difficult to match up. And then we did the low pass filter to get the output. Now let us try to see the the consequence of a mismatch in terms of phase. So over here we are trying to look at the consequence of the theta. Oscillators are not in phase synchronization. What is the consequence? V of t is m of t multiplied by cosine multiplied by another cosine, but I cannot write that as cosine squared anymore because there is a theta there. So I use a different trig identity here of multiplying two cosines, which is cosine A multiplied by cosine B is cosine sum plus cosine difference. You will hear me say sum frequencies and difference frequencies a lot today. Cosine multiplied by cosine, you got some frequencies there and difference frequency there. And then there was another m of t divided by 2 also present. If you look at these two terms individually, the sum frequencies are present at 2 omega c. So those get rejected by the low pass filter. Because the low pass filter over here is, what is this supposed to be? So if I say omega f here and minus omega f here, I want omega f to be, slightly greater than omega m, the message, but I want this to be much, much less than 2 omega c, right? So that gets rejected anyway. So that's fine, gets rejected by the low pass filter. But if you see this doesn't get rejected because this is cosine theta. So this is going to be at very low frequency. This will go through the filter. I need to worry about this now. So VO can be written as half m of t, good piece, right? That's the ideal piece. I want this. But I have a cosine theta divided by 2 also. The divide by 2 factor I can fix it by making perhaps this guy 2 there, right? H of omega, if I make that 2, I'm done. But cosine theta I need to worry about, because if theta happens to be pi over 2, then you receive nothing. VO of t becomes 0. So you see the consequence of a phase mismatch between the local oscillators being used at the transmitter and receiver. If the phase mismatch happens to be close to 0, you are fine. But if it goes towards pi over 2, you might end up with nothing. VO of t will be 0. So to keep the carriers in phase synchronization, we will need to design a complicated receiver, which will more or less use a phase lock loop to keep things in sync with respect to the phase. Frequency sync is pretty easy to achieve. Okay, so that's also an aspect of communication systems, the phase synchronization that will be discussed in detail in the higher level course. Now let's take a look at the bandwidth issue, right? Let me go back to the slide here. You guys said right here, the second aspect of things was data rate, which was related to the bandwidth, which was related to the Federal Communications Commission. So I need to worry about the bandwidth. In that, I want as high as possible for the data rate, right? So I need to make sure that whatever bandwidth I purchase from the FCC is being utilized to push as high data rate as possible. In other words, I am not wasting the expensive bandwidth resource with redundant information. Sadly, that is what happens in a double sideband suppressed carrier modulation. So what we are seeing over here is a double sideband. What does double sideband mean? Means that you can have an upper sideband and a lower sideband, and depending on how you modulated the carrier, the two things might have the same information or they might have different information. In double sideband modulation, they are having the same information. So whatever information is over here is the same information over here, which is, bandwidth wise, it is not that efficient because I'm paying for the entire frequency band here. However, I'm using only half of it for new information. The other half is redundant information. So I don't want that. Instead, I would, so because of that, people go for single sideband suppressed carrier. Suppressed carrier essentially means while you transmit, you don't see a carrier, right? You don't see this. That is suppressed, removed. That's essentially what suppressed carrier means. You don't send the carrier signal itself as part of the message. You might have to do that if you use envelope detection, asynchronous detection. If you use envelope detection, then you might have to send the carrier, because otherwise there is no way for you to recover the message. But if you use synchronous demodulation, synchronous demodulation essentially means that I have a local oscillator to demodulate at my receiver, which is what we have been observing here. All of this is synchronous detection, because I have a local oscillator being used to down convert the message to baseband. But if I didn't use a synchronous demodulation, my alternative is to use a asynchronous demodulation. I only need to track the envelope of the carrier. So I can use a simple envelope detector, basically a diode followed by an RC filter. I can just use that to track the envelope of the carrier. But that would be an asynchronous detection, asynchronous demodulation. For asynchronous demodulation, you need to send the carrier, because otherwise it cannot be detected. So in that case, it will be a double sideband modulation. In this case, with synchronous demodulation, it can be a suppressed carrier demodulation, because now I don't need the carrier to bring things down to zero, because all I need is the cosine omega ct to bring things down to zero. All right, so in terms of what we transmit, you see S of omega. It comprises of M of omega, right? So if M of t is real, it will have symmetry, Hermitian symmetry. That essentially means that whatever is here is the same as here. They are both the same information, same thing. And if I upconvert it, if I multiply it with the cosine omega ct signal, it comes over here. But in this case, the upper sideband and the lower sideband are the same thing. So why am I using 2 times omega m around omega c? 2 times omega m is what I'm using to transmit information that is only unique for omega m. That's a small, that's not as good for bandwidth efficiency, which is why people go for single sideband transmission. Single sideband essentially means remove the upper sideband or the lower sideband using a band stop filter. You can get rid of one of them using a band stop filter and then transmit the signal. That way you only have to pay for what you use, half the spectrum. All right, so let's see, upper sideband, lower sideband, we introduced that double sideband, suppressed carrier or not. And over here we have synchronous demodulation or coherent detection going on. Coherent detection means I have a local oscillator at my receiver. Now let's synchronous detection. It works very well. It actually has very, very good performance. In general, it performs much better than asynchronous detection. The problem is the receiver for that tends to be more complex. It tends to be more expensive. And the key reason for that is the synchronous, right? The need for phase synchronization between the local oscillators being used at transmitter and receiver. that is pretty difficult to achieve. So in order to work around that, things become very, very complex when transmitting and receiving. So if I was to stand at one place, let's not do that. Let's do this. If I just send the low frequency data, then I will be limited in terms of how fast I can send it. So let me actually answer that on a different slide. Not change template, add page. All right. So let us suppose that my message is this. This is omega, this is cap m of omega, right? And let us suppose that I, instead of omega, I will choose f. It might be easier to represent frequencies. So for f, I have, say, this. Okay, something like that. And I'm going to assume that this is 5 gigahertz and this is minus 5 gigahertz, right? So if this is the signal that I want to transmit, what should I choose for omega c, or I should say fc, to upconvert this signal? Well, if you wanted this to be upconverted such that it comes over here, or the least is here, right? Then you at least need 5 gig for FC. You need that to be, all of this to be upconverted to a frequency that's much higher than a 0. You see that? And there other and the higher you go to light and so on, this keeps moving forward. In general, well, there are other aspects to this as well, right? Some frequencies are, if you look at the atmospheric absorption of certain frequencies, some frequencies behave well compared to others in a manner of transmission between 2 points. So if you're curious, just try to Google atmospheric absorption of frequencies, and you will see a chart provided by the FCC that shows you what frequencies are good or versus what frequencies are bad for you to transmit using microwave frequencies. By upconverting, you increase the speed of transmission. Well, the speed of transmission, there is a speed of data being transmitted, right? So there's no speed of transmission. The speed of transmission is the speed of light. There's no speed of transmission. There's speed of data. The data itself is limited. So if you have that as your limiting frequencies of the message, that's it. That's your data. That's how far your data is. So that relates to the speed of the data rate. And in order for me to transmit that, I need a carrier in the RF frequency range, maybe hundreds of gigahertz. At least. So what I'm doing that when I do that upconversion, I am essentially increasing the bandwidth where that is located, right? The bandwidth is going to be 10 gig, no matter where it is. All right, let's move on here. Asynchronous detection or envelope detection. Over here, we desire this. M of t has to be greater than or equal to 0. Why is that? If you don't do this, then this piece will go below 0. So it will go below 0 like that. And there will be a phase reversal of the carrier, which will be reflected in a negative signs or the opposite signs in the output VO of t in comparison with M of t. You don't want that to happen, which is why you want to keep that M of t to be greater than or equal to 0. So we can fix that by adding a bias to the signal. More about that later. Which is where the suppressed carrier versus the non-suppressed carrier comes into the picture. So if M of t is greater than 0, then the desired output is the envelope, right? That's the message. The message is the envelope of the carrier, this guy. So if I want to extract that, I can use a synchronous detection, like I showed over here, using local oscillators at transmitter and receiver. Works very well. Performance is really good. Problem is that I need to have some phase lock loop to synchronize my transmitter and receiver. So over here, I'm just using an envelope detector, which is based on a diode. And what does the diode do? That is essentially going to clip off all the negative regions, right? So if I take a look at the voltage current characteristic of a diode, an ideal diode here, as I increase the voltage, my current is increasing. But if my voltage is negative, I don't have anything going through. How does that reflect? If I apply this diode, hold on. First of all, what is this? This is your LC1, LC tuned circuit. And as you change C1, you are essentially changing the resonance of the receive antenna, right? So you're trying to pick up those frequencies that are being transmitted. If you pick up the frequencies of S of omega, the first thing that you're trying to do is use a diode here, followed by R, C2, and C3. The diode is going to first get rid of all the negative regions here, right? It is going to chop off all these guys. Hence, they are not present over here. Then that signal, we are calling that as V sub A, output of the diode. VA is charging C2. So let's take a look at this. When C2 charges to VA, and when there is no voltage to supply at VA, when VA is 0, it will discharge through the resistor R. So how is that going to look like? While there is a positive cycle on VA, C2 will charge. So the red curve there, it will charge to the highest point here. And when the voltage on VA goes down, this charge C2 will start discharging through R. So we are assuming that the product RC2 is pretty high, which is why we are showing a slow decay here. And then once you have another VA, it will charge, discharge, and so on, thereby tracking the envelope of the signal S of t. And as you can see here, if I sketch this, right, if I track the red line, it almost matches the envelope of S of t. And if I wanted that envelope to be, very, very close, then I can do two things. Can you guys think of two things that you can do in order for my red line here to match up to the black dashed line in S of t? What can I do? A couple of things. Higher capacitor, sure. I can increase the capacitor or the resistor in order to make the RC time constant very large, which means that it will decay slower and slower. So that's one thing. What is the other thing that I can do? Increase the frequency of the carrier. Absolutely right. So if you increase the frequency of the carrier, these green peaks are going to come in more and more often, which means that your envelope will be a little bit more smoother to track. So that is also something that you can do. Increase the frequency of the carrier or to increase the time constant of the RC2. Next, you have another capacitor here, C3, which is essentially functioning as the DC block. It is removing the average value. DC is being removed there. So it brings down the envelope with a mean of 0. So it brings it down. So that is your message. VB is now the detected version of M of t. So pretty close, not exact, but it is able to do a job. So it is a simple detector, doesn't require a local oscillator, doesn't have a phase synchronization problem, is based on diode resistors, so it's pretty cheap. However, it does not perform as well as the synchronous detector. It is just a wave rectifier, absolutely, yes. Okay, let's see here. Now let's talk about within, so in the asynchronous detector, we wanted that message to be greater than or equal to 0. M of t has to be greater than or equal to 0. In other words, this dashed line cannot go below 0 here. It cannot cross over the horizontal axis, because otherwise there will be a phase reversal in the carrier. We don't want that to happen if we use asynchronous detection. So if we want to ensure that, then we can take a message, any message. It might be going down, it might be negative, it might be positive, whatever that is, any arbitrary message, and then we add a value B to it, some bias to it. And by adding this bias, we are pushing it up such that it will never be below 0, right? So that bias B is being used to push the signal up from here to there, right? So we are pushing it up. I don't know if I can, maybe, I don't know if this will work. No, it doesn't work. So we are essentially pushing this up such that it looks like this. Right. So we are, it has to be all positive. That's all we are trying to do here. So I need to add that bias B. Then you multiply it with the cosine to modulate the carrier, and then you transmit. So S of t now can be written as B plus M of t. Instead of M of t, now it is written as B plus M of t multiplied by cosine omega ct, where we want B plus M of t to be greater than 0. Okay. Well, Jacob asks a very important question. How good of a percentage error can you expect from a passive circuit like this? So a passive circuit like this, so percentage error, which is dependent on the signal to noise ratio, and it is also dependent on the type of modulation. It's dependent on various number of things. But in general, if I was talking about bit error rate for wireless transmission with using an asynchronous detection, I would assume any value between 10 to the negative 3 and 10 to the negative 6, which means that one error in 1000 bits or one error in 100,000 bits, 1 million bits. So that would probably be my first like a guess for an asynchronous detection for the wireless transmission. It depends on too many things. So it depends on where your phone is in the room. So for example, if you move around in a room, your phase diversity changes, and there are too many underlying things for me to be able to quantify that. Yeah. So this is an AM transmitter receiver we are talking about. Yeah, but there are lots of other things that we are not including in these diagrams. We are not including the signal processing tools, the amplifiers. There are other aspects that go into this, which we are not including, which we are kind of ignoring right now. But as you go on to better transmission schemes, the bit error rate can go, as high as 10 to the negative 14, maybe 10 to the negative 18. So when one error in transmitting 10 to the 14 bits or 10 to the 18 bits, so it can go very, very low as well. Then it becomes a problem of how long should I wait to look at one error, right? Then it becomes a different problem. All right, let's move on here. So we wanted to have the whole signal above 0, so we put a bias. So we added up a bias to it. So we are choosing B so that after B gets added on to the message, that is greater than or equal to 0, which implies that B should be greater than the absolute maximum value of M of t. So whatever value you have, after you take the absolute of the signal, whatever maximum value you have in that is your B. It has to be greater than B. So if you add such a B to your signal, then B plus M of V will be guaranteed to be greater than 0. And that's what we use to define modulation index, mu. Mu is defined as the absolute of M of t, the maximum of absolute of M of t, the message, divided by the bias, B. Mu is a value between 0 and 1, and it is often expressed as a percentage. So mu, if it is greater than 1, it's called over modulation. So you are over modulating the carrier. There are some aspects of mu that we'll take a look at right here. So suppose that M of t is some scalar k multiplied by cosine omega mt. So this is a very, very simple message. It's a cosine omega mt. And we are trying to transmit this. And S of t, the signal in time domain that we transmit, is B plus M multiplied by cosine omega ct. Mu is absolute of M of t max divided by B. In this case, it is going to be K divided by B. M of omega, the Fourier transform of K omega mt, will have two impulses, two delta functions, one at plus omega m and minus omega m. Their weights will be pi k each. So you got that. S of omega, the Fourier transform of the transmitted signal, will be B plus M of t multiplied by cosine. All right. So what is this going to look like? I can do this in two pieces actually. Let's do B cosine omega ct. B cosine omega ct will give you two impulses, one at plus omega ct, one at plus omega c and one at minus omega c, both with the weight of pi b. That is what I meant by non-suppressed carrier. As you can see here, we are sending the carrier along with the message. So in asynchronous detection, because we are trying to track the envelope in almost a cheap manner, we will have to add the bias to the signal in order to do it properly. And if we add the bias to the signal, we will have carrier being sent along with the message. So we are using the transmission power. Some of it is being associated with the carrier, some of it is being associated with the signal, which means signal is the information, right? So I'm using that power budget that I have, some of it for the signal, but some of it for carrier as well, which is not helping with the information. It's only helping with the detection. Now the other piece is what? M of t multiplied by the same cosine omega ct. That is going to give you 4 impulses, because you have 2 impulses of the M of omega being convolved with 2 impulses of the cosine. That will give you 4 impulses. Where are those 4 impulses? You got 1 here, 2 there, 3 and 4. Now at 100% modulation, that means mu is 1. What do you get? K equals B. So if k equals b, your signal is what? M of t, which is k cosine omega m t. That means the signal power in this case is going to be k squared. Carrier is k omega ct. Carrier power is going to be k squared. Why is this k? Because k equals b, right? Power in the carriers is also k squared. So at 100% modulation, you get signal power equals carrier power. At 50% modulation, so what does that mean? That means that I'm sending half of the power that I'm transmitting is for the signal, half of it is for the carrier. At 50% modulation, which means that mu is half, that means the bias is 2 times k, where k is the highest value in m. Carrier power becomes 2k squared, which is 4k squared. Signal power remains as is. So in comparison now, signal power is essentially 25% of carrier power. So we are sending a huge carrier and quarter of that power is associated for signal, which is, pretty bad, right? Because we are using most of our power resource to transmit something that doesn't even have information, the carrier. It is just being used for the detection. So we would try to keep that mu factor, the modulation index, between 90 and 95%. Pretty high, pretty close to 1. All right. So what we'll do here is, because what we have next is a new topic, I'm going to stop here.